design. So topic 10, chapter 13, concrete form design. So this is the last topic of this course. And today we are going to cover this topic. So the basic design principle for the concrete form design is that the design of concrete formwork that has adequate strength to resist failure and will not deflect excessively when the forms are filled is a problem in structural design. So unless commercial forms are used, this will usually involve the design of wall, column, or slab form constructed of wood or plywood. So the question is, what is the reason why we are considering the design of the formwork? Normally, the formwork are commercially available, and for certain types of constructions, we can perform we can use those commercially available formworks. So these formworks are used to support the concrete when the concrete is poured in the walls, or to support the concrete also when the concrete is poured into the slab. However, if those commercially available forms are not available, then in many cases you have to use wood-based formwork. That means the formwork based on the formwork from the wood or plywood to be made. So those wooden-based formwork or the plywood formwork may need to be properly designed for use in the concrete. So when the concrete is placed on those formworks, so the concrete has the loads, and under these loads, the formwork can deflect. And therefore, when we want to design those formworks, our objective is there should not be excessive deflection, and the formwork is free from the different types of failures, which are the bending failures and the shear failure. So these formworks needs to be designed. So these forms are constructed of wood or plywood. So in this topic, we are considering the forms which are made from wood or plywood. So what are these different types of forms? So they have the slab forms, they have the wall forms, they have the column forms, etc. So in such cases, after the design loads have been established, each of the primary form components may be analyzed as a beam to determine the maximum bending and shear stresses and the maximum deflection that will occur. So vertical supports and lateral bracings are then analyzed for compression and tension loads. So when talking about the design principles, then the forms can be analyzed considering them as components of the beams, okay, as beams, etc., as a beam element. So when you do the design in a structural engineering course, you may have learned the design of the beams. So we may consider those forms as the beams to analyze them for their maximum bending and shear stresses and the maximum deflection that will occur. Okay, so once those proper members for the formwork have been selected, proper sections have been selected, we need to provide them the supports as well. So these can be the vertical supports and these can be the lateral support. So therefore, The design of formwork also involves various steps, such as the design of the member itself and the design of the proper support. Okay, so when we want to design the forms, we have to consider the different types of design loads. We have to consider different types of design loads. So these design loads we can consider first of all for the wall and the column forms. So for example, if we have the vertical forms, that means the forms which are used for the walls and the columns, the design load consists of the lateral pressure of the concrete against the forms. So for example, when there is a vertical form and over here, the concrete will exert lateral pressure. Okay. So the concrete can exert lateral pressure. So for example, if so if the concrete is placed over here, so the concrete can exert a lateral pressure. Okay. I think it's not very convenient to draw it over here. Okay, so concrete can exert lateral pressure. So what is the lateral pressure? So for this, for all columns and for walls with the vertical rate of placement less than 2.1 meter per hour and a placement height of 4.3 meter or less. So we can exert the lateral pressure by these equations. So so when the concrete is being placed into the formwork at some pressure, so depending on how the concrete is being placed, the pouring rate, and depending on the height of the wall, the lateral pressure can vary. So this will, for this, there are certain equations which can be used, and these equations are given in the ACI code, okay, American Concrete Institute codes. So two types of equations are used. One are in the the first equation is in the US customary units, and the second equation is in the one shown in the square brackets is in the SI unit. So we can use these equations in the square bracket. So this equation, according to this equation, the lateral pressure on the form can be given by this equation, which is equal to CW CC 7.2 plus 785 R over T plus 18. So where these parameters are, what are these parameters? So where CW is the unit weight coefficient. So it is not the unit weight, it is the unit weight coefficient. So this depends on the unit weight of the concrete. Okay, unit weight of the concrete. That means the density of the concrete, kilogram per cubic meter, in terms of in the units of kilogram per cubic meter. And Cc is the chemistry coefficients. That means what is the type of the concrete, type 1, type 2, type 3 concrete, cement, type 1, type 2, type 3 cement. So some of the cements are rapid setting cements. Some of the cements are not rapid setting cement. Some of the mixtures include the slags. Some of the mixtures include the fly ash. So use of these other admixtures into the concrete will retard or accelerate the setting time of the concrete. So depending on that, some of the coefficients may be added. P, as it was shown in previously, P is the lateral pressure. So pressure, the units of pressures are kilopascals, okay? Newton per square meter, or we can convert it into the kilopascal units. R is the rate of vertical placement. So at what rate the concrete is being poured over here, okay? At what rate? So that means the concrete is being slowly or at a very fast rate. And T is the temperature. T is the concrete temperature. So as you can see that from this equation, higher the temperature of the concrete, so this factor will reduce, and then the pressure will also reduce. So because at higher temperature, the concrete will set rather quickly, so the pressure, lateral pressure for the design may be reduced over here. And then there are some other certain other terms as well, which we will use later. H is the height of the form. W is the unit weight of the concrete, okay? And when we calculate this pressure value from this equation, this pressure value should not be less than 600 C times W, 600 CW or 28.7 CW kilopascal, or the maximum pressure cannot be more than WH, that is the weight of the concrete itself. So that means the original pressure will be somewhere between these two limits, 28.7 CW times WH. Okay, so remember that some of these coefficients, so for example, 600 over here and 785 or T plus 18, these coefficients have been empirically determined. Okay, and these are the equations given by the code. So we have to consult those codes for the given equations to use them into the design. So this equation then just simply determines the lateral pressure on the vertical forms. Okay, and then this lateral pressure have to be between this minimum and the maximum pressure. The maximum pressure will be, as you can see that, it can be given by the W times the height. So for example, more is the height, and then height has to be multiplied by the unit weight, and then that will be the vertical pressure. So this is like more like considering the concrete as a complete fluid, okay? Then its total weight is being used to determine the lateral pressure. Okay, next is there are some other equations as well. So remember that, well, we have introduced this equation, but this equation is for that situation when the vertical rate of placement is less than 2.1 meter per hour. Okay, vertical rate of placement is 2. less than meter per hour, and the placement height is less than 4.3 meter. However, if these conditions are not meeting, then we have to use another equation. So for walls with the vertical rate of placement between 2.1 to 4.6 meter, and walls with the rate of placement less than 2.1 meter, whose placement height exceeds 4.3 meter. Okay, so for these two conditions, that means if the placement rate is higher than 2.1 meter, then we can use this equation. And if the placement rate is not higher than 2.1 meter, but the height is higher than 4.3 meter, then we can use this equation. So In those situations, as you can see that the lateral pressure is going to be increased because either the height is increasing or the placement rate is increasing. So compared with the previous equation, there is one more term, 785 R over T plus 18. And then there is this term 244 R over T plus 18. And then one more term has been added, 1154 over T plus 18. These two terms have been added. That is the only difference between these two terms. Okay, so CW, CC, and then how we will calculate the CW and CC, that we can calculate from two tables. And just like for the previous equations, the calculated value of this lateral pressure should be between these minimum pressure and the maximum pressure. Okay, and for the calculation of the CW, we can use this table 13, table 1. So because CW was the unit weight coefficients, the unit, so W is for the weight, unit weight. And the unit weight coefficient we can use for the situations when we know the density of the concrete. So if the unit weight of the concrete is less than 2243 kilogram per cubic meter, 2243, so it is slightly on the lighter side, then this coefficient CW can be calculated by this formula, 0.5 times 1 plus W over 2323. W over 232. So W is the actual unit weight, okay, which is less than 2243. So when we calculate it, whatever the value we get, but this value should not be less than 0.8. So if it is coming as less than 0.8, we will take 0.8 value. On the other hand, if the weight is between 2243 and 2403 kilogram per cubic meter unit weight, we can safely use CW as 1. Okay. On the other hand, if the unit weight is over 2403, so then the CW should be more than 1. So it will be W over 2323. Okay. So we can use W over 2323. So this is the unit weight coefficient CW, which is used in these lateral pressure formulas. So the other coefficient C is CC, which is the chemistry coefficient. It depends on the type of the cement used. So concrete chemistry coefficient, so cement type or blend. So if it is type 1, type 2, or type 3 cement, which is used without any retarder, so then we will use 1. If it is type 1, type 2, or type 3 cement, which is used with a retarder, we will use 1.2. So because when there is a retarder, so the concrete will set at a slower pace. So therefore, accordingly, the lateral pressure on the form, the effect of the lateral pressure on the form will be more. So therefore, CC will be greater. And similarly, for the other cases, when other admixtures in the form of the slag or in the form of the fly ash are used, so CC coefficient is more than 1. So for example, if it is less than 70% slag or 40% fly ash without retarder, then it is 1.2. And if also, on the other hand, if slag and retarder are used with slags and fly ash are used with the retarder, so we can use 1.4. And similarly, blends containing more than 70% slag or 40% fly ash, then again 1.4 CC coefficient should be used. Okay, so this is all of this discussion is for the lateral pressure. Okay. Similarly, for walls with a vertical rate of placement greater than 4.6 meter per hour. Okay. So remember that we have considered two equations before. So this equation was for the rate of placement of 2.1 to 4.6 meter per hour. And the first one was for rate of placement for 2.1 meter per hour. Okay, so 2.1 less than 2.1 meter per hour, this equation. From 2.1 to 4.6 meter per hour, this equation. But if the rate of placement is more than 4.6 meter per hour, then we will take this concrete as just like a fluid. Okay, so then the pressure can be simply calculated by WH. Okay, so for walls with a vertical rate of placement greater than 4.6 meter per hour, or when the forms will be filled before the concrete stiffens, so we will use rho is equal to, that is pressure is equal to W times H. So simply we will use this equation. In other conditions, when the forms are vibrated externally, it is recommended that the design load twice that given by equation 13.1 and 13-2 be used. Okay. So these 13-2, this equation, and then 13-1, this equation, and then 13.3, this equation. These equations are for those situations when the concrete is poured into the formwork and then the concrete is internally vibrated. Okay, but in some other situations, the formwork can be externally vibrated as well. So when the formwork is externally vibrated, then the pressure exerted on the formwork will be much higher. So in those situations, it is recommended that whatever the value is calculated from the previous equation, that value is doubled. Okay, in the equation from double compared with equation 13.1 and 13.2, that should be used. And when the concrete, on the other hand, when the concrete is pumped into the vertical forms from the bottom, that is the bottom column and the wall forms, equation 13.3 should be used, and a minimum additional pressure of 25% should be added to allow for pump surge pressure. So when the concrete is being pumped from the bottom in the both the column and the wall forms, then whatever the pressure value which you calculate from equation 13.3, 25% more of that should be used. Okay, so this was about the pressure calculation in the wall or column forms. So now we can consider the situation for the floor and roof slab forms. Okay, so is it clear up to now? Do you have any questions?
No questions.
Okay. Next, now we are after the wall and the form, we can consider the floor and wall and the columns. We can consider the floor and roof slab forms. Okay. So the design load on the floor and the roof slab forms are different from the design loads on the floor and the roof slab forms are different from the walls and the columns. Because in the walls and the columns, the concrete will vertically and the pressure will be horizontal on the forms. Whereas in the floor and the roof slab form, the pressure will be vertical. So that vertical pressure will come from the weight of the whatever the weight the form is supporting. So the design load to be used for elevated slabs consists of the weight of the weight of the concrete and reinforcing steel, the weight of the forms themselves, and any live loads, equipment, workers, materials, etc. Okay. So now let's consider these different loads one by one. So first of all, the weight of the reinforced concrete itself. So for normal reinforced concrete, the design load for concrete and steel is based on a unit weight of 150 pound per cubic feet, or 2403 kilogram per cubic meter. So 2403 kilogram per cubic meter, okay, is the normal figure which is used for the weight of the concrete. The American Concrete Institute, ACI, recommends that a minimum live load of 2.4 kilopascal should be used. A minimum live load of 2.4 kilopascal. So live load is because of the people walking on the formwork, the equipment moving, etc. Okay. So used for the weight of the equipment, materials, and workers. Okay. So the dead load is 2403. Dead load will be based on 2403 kilogram per cubic meter, and then we can multiply it with the area or the length, and the live load is based on the as given by the codes. So on the other hand, of course, we may need to do some adjustments as well. So for example, when motorized concrete buggies are utilized, that means some concrete buggies are used on the formworks. So then the live load should be increased to at least 75 pound per square foot, or it is about 3.4 kilopascal. So normally the live load is taken as 2.4 kilopascal, but when motorized concrete buggies are used on the formworks, then live load can be increased to 3.6 kilopascal. And in addition, if there are any unusual loads, that will be in addition to these values. Similarly, ACI also recommends that a minimum design load of 4.8 kilopascal be used. So that means when you calculate the live load plus the dead load, the live load plus dead load should not be less than 4.8 kilopascal. Okay. So for example, if you calculate the live load to be 2.4 kilopascal and the dead load to be 1.2 kilopascal, 1.2 plus 2.4, that is 3.6 kilopascal. You will not use 3.6 kilopascal. This you will use at least 4.8 kilopascal as the live load. So this is just to remain on the safer side, and it is recommended by the code. So this should be increased to this. That means this minimum should be increased to 6 kilopascal when motorized buggies are used. Okay. That is, when motorized buggies are used, it should be increased to 6 kilopascal. Okay. So these were the vertical loads. Of course, there are also the lateral loads as well. So the lateral loads, such as those imposed by wind, the movement of the equipment on the forms, and the placing of the concrete into the forms, are due to these reasons, are the reasons for the lateral loads. So the minimum lateral design loads recommended for tied wall forms are given in table 13-3. Okay. And when the form ties are not used, bracing must be designed to resist the internal concrete pressure as well as internal loads. Okay. So when the wall ties are used, that means the walls are internally. So for example, when the walls, for example, here, if these two are the forms, and then these two forms are tied together by some lateral support internally. So these are the ties. So when internal ties are used, so then we can use the values given in table 13-3. Okay. And then when the form ties are not used, bracing must be designed. So when these ties are not used, then the external supports must be provided. Okay. External supports must be provided. Okay. So the external ties are used. So the bracing which are the external supports must be designed to resist the internal concrete pressure as well as the external loads. Okay, so what does this table 13-3 shows us? So table 13-3 shows us that the recommended minimum lateral design load for the wall forms is given by this. So when the lateral force applied at the so for example, if it depends on uh, the recommended minimum lateral design load for wall forms. Okay, that means uh, these wall forms would be designed for these design loads. So it depends on the height of the wall. For example, if the height of the wall is less than 2.4 meter, then the design lateral force applied at the top of the form should be H times WF over 2. Okay, so where WF is the wind force prescribed by the local code. Okay, so the local codes will prescribe this wind force. Okay, which will be uh, given in the kilopascal units, but it should be a minimum of 0.72 kilopascal. Okay, H times WF by 2. If the wall height is 2.4 meter or over, but less than 6.7 meter, then at least H times WF by 2 should be used. Okay, that means it can be 1.46 or H into W. So whichever is the higher. Okay, whichever is the higher, 1.46 or whichever is the higher. Or if the wall height is 6.7 meter or above, it should be 0.358 H or at least H times WF by 2. Okay, so this is the situation which we can use. So the minimum lateral design loads for the walls. Okay, so later on we will see in the examples the use of these equations, and then it will be much more clear. Okay. For slab forms, the minimum lateral design load is expressed as follows. So H is equal to 0.02 times dead load times WS times WS. So this X is actually the multiplication symbol. So where H is the lateral force applied along the edge of the slab, which is given in kilonewton per meter. Minimum value should be 1.46 kilonewton per meter. DL is the design dead load, which is given in kilopascal, and WS is the width of the slab perpendicular to the form edge. So in using equation 13-4, design dead load includes the weight of the concrete plus the form work. Okay, so the dead load means the weight of the concrete plus the form work. In determining the value of the WS, consider only that part of the slab being placed at one time. That means at one time, whatever part of the slab you will place, it is not like the full slab width. It can be the part of the slab which can be placed at one time. So later on, we will also have the application of this equation. Okay, so the method of analysis. Okay, so how we are going to analyze these formwork designs. What is the basis? So after appropriate design loads have been selected, the sheathing, joists or studs and stringers or wales are analyzed in terms. Considering each member to be a uniformly loaded beam supported in one of the three conditions: a single span, two span, or three span or larger, and analyzed for bending, shear, and deformation. So this is the basis of the analysis, which means that if I can, okay. So this basis of the analysis can be used. Okay, so let's see it in the, because I did not, and let's see it in the chapter itself. Okay, so this is the chapter. So here these equations have been explained and the basis of the design. Okay, analysis method. So we have to see this figure first. Okay, so this is the figure for the design analysis of the form members. So first is the sheathing. That means the sheathing. Sheathing is the like a slab. That is the part of the formwork which supports the slab. So, for example, this thin sheet. Okay, this thin sheet is the sheathing, and this thin sheet is being supported on two sides by the beams. We call these beams as the joists. And in this case, these joists are at a spacing of, at a center to center spacing of L1. Okay. And on this sheet, there is a load W1. Okay. There is a load W1. And here, if we on this left hand side, we consider the section of this sheet about 1 feet or 1 meter wide for the purpose of our analysis. So therefore, here we can see that the W is the design load. Okay, W is the design load. That is whatever the design load which we will calculate from the previous equations. And then we will multiply it with 1, which is 1 is for the we take the for the convenience, we take the width for the design as width for the slab as 1 meter. So in this case, if the design load is in kilonewton per square meter, so W1 will be in terms of the kilonewton per meter. So, and then we have this that is the joists. That means the joists in turn are supported on the stringers. So the stringers are also beams, but the stringers are slightly larger beams than the joists. So this is the system which is used. So we have the sheets. Sheets are supported on the joists. Joists are supported on the stringers. Joists are supported on the stringers. So here we are looking at the design of the slab formwork. Okay, and then the joists are and then the stringers are supported on the shores, which are the vertical supports. So therefore, if we are given in a problem, if we know that we are going to use a certain type of sheath, that means if we have available a certain type of sheath, maybe 1 inch thick or 25 millimeter thick sheath, and if we have, say, 50 by 200 millimeter section joist, if we have 100 by 200 millimeter stringer, or if we have certain types of shores available, if the material is available, then what we have to determine is the appropriate spacing between those joists. Okay, the appropriate spacing between those stringers, the appropriate spacing between those shores, and that will complete our design. That will complete the design. So this is the design situation. Okay, so in the slab form design, then we can perform such a method of analysis, and then relevant informations have been given over here. So what I can do is I can go through the example, and with that example, then I will explain the steps. As you can see that a lot of tables and the data has been given, which will be used in those analysis. Okay. So yeah, this is the example one. I will look at this example. Okay. Do you have any question? Hello. Are you here? Is anyone here? So we are going to start this example one. Hello. Okay. So let's start this example one. Okay. So what does example one say? It is the design the formwork that is this which is given in this figure two for an elevated concrete floor slab which is 152 millimeter thick. Okay, 6 inch or 152. Of course, both types of units are given, but I will be following along the SI units. So sheathing will be nominal 1 inch or 25 millimeter lumber, while 50 by 200 millimeter lumber will be used for joists. Stringers will be 100 by 200 millimeter lumber. Assume that all members are continuous over 3 or more spans. Commercial 17.8 kilonewton shores will be used. It is estimated that the weight of the formwork will be 0.24 kilopascal. The adjusted allowable stresses for the lumber being used are as follows. That means the stresses in the lumber should not increase these limits. So for example, FB is the bending stress. FV is the shear stress. FC is the compressive stress in the perpendicular direction, perpendicular, and then FC is the compressive stress in the parallel to the grain, and E is the modulus of elasticity. So these are the limits which have been given to you. So the maximum deflection of the form members will be limited to L by 360. That is, whatever the span divided by 360, that will be the maximum allowable deflection. So use the minimum value of live load permitted by ACI, okay, which is about 2.4 kilopascal. Determine the joist spacing, stringer spacing, and shore spacing. So as I have just explained it before, the purpose for this type of analysis when certain sections have been given is that we have to determine the appropriate spacing between the joists, stringers, and the shores. So here we have this type of situation. So we have a sheath over here, okay? Sheaths are supported by the joists. Joists are supported by the stringers. Stringers are supported by the shores, okay? So here in the case of the plan, we have the shore here, we have the stringer here, we have the joist here, and then we have the sheathing here. So this is a kind of like 4-component system. So what we have to determine is we have to determine the spacing between the joists. That means we have to determine the spacing between the stringers. Okay. So determine the joist spacing, stringer spacing, and the shore spacing. Okay. So this thing we need to determine. So based on this, the given information, so we will start it. So first of all, first step will be to calculate the design load. Okay. So assume the concrete density is 2403 kilogram per cubic meter. Okay. So this is for the normal concrete. Okay. So if it is not mentioned that what type of concrete we are assuming, so we will use that we are using a normal weight concrete for which the standard value is 2403 kilogram per cubic meter. Okay. So for this normal weight concrete, the dead load will be given by this. So let's look at only the values given in these square brackets. So because the values without the square brackets are in the US customary unit. So our preference will be is for the SI units. Okay. So if we have this density of concrete 2403 kilogram per cubic meter, then we take a section of the concrete 1 meter by 1 meter wide by 1 meter tall and multiplied by 0.152 millimeter thick, because the slab thickness is 152 millimeter. Slab thickness is 152 millimeter. So 152 millimeter means 0.152 meter. So 2403 multiplied by this total volume. So that is the total weight. Okay. And of course, and we don't need to add this one by one, so that we have this as this weight as a pressure. But remember that this is the kilogram per cubic meter. Okay, so in this kilogram, so to convert kilogram into newtons, so we have to multiply it by 0.0098. Okay, so we have to multiply. So therefore, this 0.0098 will be multiplied to convert the units from the kilogram to newtons. Okay, so that's why we will get the units of kilopascal over here. So in this case, we get a live load of a dead load of 3.58 kilopascal. That is this is not the only dead load. The other dead load is the weight of the formwork, which is given here. Yeah, we will use 0.24 kilopascal, which is the weight of the formwork itself. And the live load is the use the minimum value of the live load permitted by ACI. So as it was explained before that the minimum live load typical value is 2.4 kilopascal. So we are not using any motorized buggies over here. So we are not going to increase it to other value like 4.8 kilopascal or 3.6 kilopascal. So we are just using a normal value. So add all these three together. So the design load is 6.22 kilopascal. So in this case, the design load we have calculated as 6.22 kilopascal. So we will use this design load of 6.22 kilopascal for further analysis. Okay. So we have calculated the design load. As a next step, we will calculate the deck design. So consider a uniformly, the deck design means the deck consists of the sheathing, joist, stringers, and of course the shore. So we will go one by one. So first we will consider the sheathing. So for the design, we will go from top to bottom. But when we are doing the construction, we will go from the bottom to top. Okay. So consider a uniformly loaded strip of decking or the sheathing, 12-inch or 1 meter wide, placed perpendicular to the joists. That is in, if you can see that figure 13-1A. In this figure, in the previous figure. Anyway, so and analyze it as a beam. So assume that the strip is continuous over 3 or more spans and use the appropriate equations of table 13.5 and 13.5a. Okay. Now, just consider that we are starting from the sheathing, okay, because it is the sheathing which is on the top, okay. So for the sheathing, we have this design load of 6.22 kilonewton per square meter. So, and that sheathing load will go on the joists, okay. Sheathing load will go on the joist. So we will assume that we will assume that this sheathing will be placed on the joist. So that we will take a 1 meter width of the sheathing, and that will go that we will consider. Okay, that is we'll consider a 1 meter width. That means if we take this as the plane of the paper perpendicular to this plane, okay, we will take 1 meter width. So 6.22 kilonewton per square meter multiplied by 1 Newton. So it will be 6.22 kilonewton per meter. That is the weight on the sheathing. Okay, weight of the sheathing. So for this weight on the sheathing, now we have to determine how that is that now we have to determine this. For example, this sheathing is being placed on these two joists. So whether we will place the joists at this much distance or slightly more distance, we need to determine it. So that means we need to determine the span length. So this span length can be determined based on 3 criteria: bending criteria, shear criteria, and the deflection criteria. By the bending criteria, it means that there will be a load over here, and then this slab will bend, and at some point the bending stresses will be such a magnitude that the slab will fail. Okay, and in the case of the shear, then the shear stresses will be such greater that the slab will fail in the with the shearing force. Or in the deflection will be excessive, that it will be more than our required limit. So we will determine this span length based on these 3 bending criteria. So for this, we will need to use the appropriate equation. So what are these equations have been provided in table here. Yeah. In table 5 and 5A. So 5 is for US customary units. So we will use table 5A, which is for the SI units. Okay, so for this, we will see that the design conditions are bending, okay, and whether it is a wood or a plywood. And then second design condition is shear, under the shear, whether it is a wood or a plywood. And the third design condition is the deflection, and under the deflection, which type of deflection we are using, whether we are using L by 360, L by 240, or L by 180. And then another design condition, and the 2 other design conditions are for the compression and the tension. Okay, so for this, we will use this first equation, and then each of these design conditions have been provided for the support conditions. So in the current situation, we are assuming that each of these joists and the stringers have 3 or more spans. Okay, 3 or more spans. So that means we will use the equations in this column over here. We will use this first equation over here from here for the joists. Okay, it is 40.7 over 1000 times D, which is FBB over W. So where D is the effective thickness of the sheet, and FB is the allowable bending stress. B is the width, and W is the design load, which we just calculated as 6.22. So we will use this equation over here. Okay, and then let's see if we have the same equation over here. Yes, so 40.7 over 1000 into D into FB into B over W power 1 by 2. Okay, so 40.7 over 1000 is from the formula. D is equal to 19 millimeter. Okay, so why is it 19 millimeter? Remember that we are using for a sheath, and the sheath we are using is 25 millimeter thick. But remember, but this 25 millimeters is the nominal thickness. 25 millimeter is the nominal. So for this nominal thickness, we need to look at this table. Okay, remember that we are using here. Design the formwork for an elevated concrete slab thick sheathing will be nominal 1 millimeter lumber. Okay, nominal 1 millimeter lumber. So for example, for nominal 1 millimeter, okay, and so nominal 1 inch over here, if you see these tables, for a nominal size of say 1 inch, the actual size is in millimeter is 19 millimeter. Okay, so in the formula we will not use the nominal size, we will use the actual size. So 1 millimeter is actually 19 millimeter. Actually, one inch is actually 25 millimeter, but that is nominal. The actual size is 19 millimeters. So that will be used over here. Okay, so here, if you have over here, so 19 millimeter has been used. FB is the allowable bending stress 7412, so which is given over here. Yeah, for the sheathing, allowable bending stress is 7412 multiplied by the width. So we, in this case, for the sheathing, we have taken the width as 1000 millimeter. That is 1 meter wide width. And then W was calculated to be 6.22 kilonewton per meter. Okay. So here you can see that we have to be very careful for the units. Okay. For the length units, we are using in millimeters. Okay. So here we cannot take like 1 meter over here. So we will use it in millimeters. And then we have to be careful about the units. So the pressure units is in kilopascal. So kilonewton per square meter. So in this case, we get, if you will calculate it, you will get a value of 844 millimeters. So this is one value which we will get. So the other value we will get from the shear condition. And for the shear condition, we will use this equation. And for this, we will again go back to table 13 table 5a. So for the shear condition, we have this for 3 or more spans, 1.11 over 1000 FVA over W into 2D. Okay. Okay, so here we have over here is yeah 1.11 FVA over W plus 2D. So 1.11 over 1000 is from the formula. FV is the allowable shear stress, so which is 1200. Okay, which is 1200. A is the area. So area will be like width times the thickness in this case. So 1000 times 19 millimeter. Okay, because earlier we used these 19 millimeter over here, 1000 over here. And W is the 6.22, which was already calculated. 2 times D, 2 times 19. So it will be 4117 millimeter. 4117. So if the shear requirement is to be met, so this span can be 4107 millimeter. But if the bending requirement is to be met, this span should be 844 millimeter. Okay. And the third condition is the deflection. So for the deflection, we will use this equation, 73.8 over 1000. So again, we will go back to this table 5a. And in the statement of the question, it was said that the deflection will be limited to L by 360. Will be limited to L by 3. So for L by 360 and for 3 or more span cases, we have this equation L over 73.8 over 1000, EI over 1 by over 3. Okay, 73. So, okay. So then here, 73.18 over 1000, this comes from the formula. The value of E is 9.4 into 10 to the power 6, so which is given over here. Yeah, 9.4 into 10 to the power 6, which is given over here. And the I, the value of I. So I is the inertia, okay? (9.4 into 10 to the power 6 into I is the modulus of elasticity. Okay, so yeah, I is okay. In this case, I is the second moment of inertia area. So if you remember the formula from your structural analysis course, its formula is BH cube over 12. So B is the width, okay, and 19 is the height, or divided by 12. So that formula has been used directly over here. 1000 into h cube over 12 and divided by 6.22 and then power 1 by 3. Okay, so yeah, BDH cube over 12. So it was 703 millimeter. So in this case, we get three values of the spans: 844 millimeter, 4107 millimeter, and 703 millimeter. So in this case, the minimum value will control. So in this case, the minimum value, that means if the, for example, if we take for the bending condition 844 millimeter span, the span will be more. If the span will be more, deflection will be higher. So that is not acceptable. So therefore, this deflection will govern in this case, as the maximum allowable span is 703 millimeter. So for a modular value, we can take 703 millimeter is equivalent to 27.7 inches. So close to 27.7 inches, a modular value is, a rounded value is 24 inch. That can be taken. So instead of 703 millimeter, we can further reduce it to 610 millimeter joist spacing. So therefore, one component of the design we have calculated as the joist spacing, which is 601 millimeter. Okay, 610 millimeter. So that means the joist spacings will be 610 millimeter. Okay, so this will be the joist spacing. Next, we will calculate the stringer spacing that will come in the joist design. Okay, so this was about the sheathing. For the sheathing, we calculate the joist spacing. That is the that is the supports which will be provided to the sheathing. So for the joist, we will calculate the stringer spacing. So for this, again, we will have to perform the calculation. So first of all, because now we have chosen 610 millimeter as the spacing, and the load is 6.22 kilopascal. So that load 6.22 kilopascal will be now used for 610 millimeter of spacing. So in this case, the load for this purpose, the load for the design, joist design will become 6.22 multiplied by 0.61 meter. In this case, that is 3.79 kilonewton per meter. And then similarly, we will calculate the lengths for the bending, shear, and bending, shear, and deflections. But however, we will need to use the appropriate equation, which is not the same as we used for the previous case. In the previous case, there was a D over here. So because sheathing is just a sheath, so the first equation in this table 5a, the first equation is for the sheathing. The second equation is for the beams or the joists or the stringers. So we will use this equation 100 over 1000 FBS over W. Okay, so we will use this equation. Okay, so again, in the joist design, we will use this equation 1000. FB is the allowable bending stress. Allowable bending stress is now, we will use this one, 8619. Okay, this is for the other members, 8619. Yeah, 8619. And what is the value of S? Okay, S is the section modulus. Okay, so the section modulus is given as 2.153 into 10 to the power 5. That we will see from the table. Remember that in this example, we are using a 2 by 8 inch joist. Okay, so in this table, which is table number 7, 2 by 8 inch joist is here, and its section modulus is 2.153 into 10 to the power 5 millimeter cube. Okay, so S is the section modulus. So S is the section modulus we can use here, 2.153 into 10 to the power 5, and divided by W, which we calculated over here, and this gives us 2213 millimeter. So this is the length based on the bending. And now for the shear, we have to use this equation. And again, we need to consider that table 5a for the appropriate value. So here you can see that 1.11 over 1000 is from the formula. Allowable shear stress is 1241, which is from here. Okay. And A is the area. So this area 7016, we will see from this table 7. So this is 2 by 8. And the area is 7.016 times 10 to the power 3. So it is 7016. The area is 7016. Okay, divided by 3.79 plus 2 times D. Okay, so D is the depth, vertical depth. D is the vertical depth. So it is actually a 200 millimeter section, right? In this, say it is, but that is the nominal. Okay, so for this 2 by 8, okay, so for this 2 by 8, yeah, so for this 2 by 8, the actual size is 38 by 184. So we will use this 184, not 200 millimeter. Okay, so 2 by 8, 2 by 100. So it is 2918 millimeter. Okay. And next is the requirement for the deflection. So we can use this values of E value is from here. And I is the moment of inertia. So the moment of inertia we can calculate also. We can see from over here. The moment of inertia is from table here. Yeah, the last column 2 by 8. It is 19.83 into 10 to the power 6. Okay, 19.83 into 10 to the power 6. Yeah, and divided by 3.79. So we get 2732 millimeter. Okay, so in this way, we get this value for, so we get three values, 2732 millimeter, 2918 millimeter, and what 2213 millimeters. So in this case, the bending goes because its value is the minimum. So the bending goes and the maximum joist span is 2213 millimeters. So which is close, which is 87 inch. 87 inch is closer to 84 inch. So which is about 7 feet, and 2134 millimeters. So we will select a stringer spacing of about 2134 millimeter. So in a similar way, we can design, do the stringer design, which is which will be using the same set of equations. But remember that the stringer section is not 2 by 8, stringer section is 4 by 8. Yeah, 4 by 8. So we will use the properties of 4 by 8 sections in this table. Okay. Yeah. For the joists, we use the properties of 2 by 8. For the stringer, we will use the properties of 4 by 8. Okay. So you will calculate it for bending. You can go through it, and then it will be, you will understand it. So in this case, the bending will go on, and the maximum span length will be 1808 meters. So in this case, we can see that the stringers will be much, the stringer spacing, that is the, not the stringer spacing, the span of the stringers will be bending goons, and the maximum span will be, in this case, will be 1808 millimeter, because here we can get that for the bending we will get 1808 millimeter, for the shear 2070 millimeter, for the deflection we will get 2388 millimeter. And then at the last step, we will check the shore strength before selecting the stringer strengths, because the shores we are using are 17.8 kilonewton. Okay, and we have 13.25 as the now we must check the shore strength before selecting the stringer span. The maximum stringer span based on the shore strength is equal to the shore strength divided by the load per unit length of the string. So the load per unit length of the stringer is 13.25, which we actually calculated over here. Yeah, for the stringer. Okay, so if we divide this load by the shore capacity divided by this load, so we'll get a spacing of 1.343 millimeter. So which means that earlier we calculated it to be 1808 millimeter, but the shores which we are using may not support this much big length. So therefore, the shores must be placed at 1.343 millimeter. So 1.343 millimeter is 52.7 inches, which is closer to 48 inches. So maybe we can use a 4 feet width of the shores in this case. And then as a final check, we will calculate the punching shear stress as well, because for example, the shore because the joists and the beams will, that is the, this is the, if this is the joist, this is the stringer, the joist will be supported on the stringer. So at this place, sorry, at this at their intersection, joist and the stringer, there may be a contact area, and then some punching failure can take place as well. So for final step is to calculate this punching failure, and then this strength must be also met. So their bending, the stress at the bending area is 2392 millimeter, which is less than the given 2792 millimeter, 2792 megapascals stress, which is needed over here. Okay. So the final design over here is that the decking, the nominal decking will be 1 inch, 25 millimeter lumber. The joists will be used as 610 millimeter spacing, and the stringers will be used at 2.13 meter spacing, and the shores will be used at 1.22 meter interval. So these are the final design parameters which can be calculated over here. Okay, so with this, we have completed this example one. Then I think in the next class, we will continue with this other two examples, which will talk about the wall and column designs. Okay. So we will continue this topic in the next lesson, and hopefully we will complete it in the next lesson. Do you have any questions?